Hello everyone, I'm Mohsen Zakir Istiqamati. Unfortunately, I could not physically be in the meeting, but I hope this video could serve as a virtual greeting. We are very excited to have you join us in this special group discussion. So, without any further ado, as we know, a successful machine learning model development creates correct, robust, unbiased, and interpretable models. Here, correctness refers to machine learning models only including parameters that actually affect the model performance. Commonly, researchers use feature importance and penalty approaches to determine and remove redundant parameters from machine learning models. On the other hand, robustness is when machine learning models do not provide reliable estimate for anomalous data. And this anomaly can happen in modeling or observation. Often, robustness is checked through data quality control and assurance. In some sense, bias in the machine learning models is due to anomaly as well, where this anomaly happens in the input data. However, today I would like to pose the question on the last feature, interpretability of machine learning models. One of the most common opposing arguments is that machine learning models are black box, meaning that the fate of input parameters is unclear as soon as the mapping procedure begins. However, I would like to argue that machine learning models do not necessarily need to be a black box. Researchers develop different techniques in statistics and computer science to interpret machine learning models, such as Shapley, partial dependence plus, and accumulated local effects. Now let me introduce this great book by Christopher Molnar, which talks about methods for interpretation of machine learning models. Also, as a side note, the author made this book available to the public for free, which you can find on GitHub. Now, in this book, the author suggests that from one perspective, we can classify these interpretation techniques as either local or global, where local methods help us to study small portions of larger machine learning models. And in contrast, global methods are better suited to interpret the machine learning model as a whole. For example, a local interpretation may look at a small part of a neural network, whereas a global interpretation will visualize the weight distribution in the entire network. From another perspective, we can classify these techniques as either model-specific or model-agnostic, where the model-specific techniques are helpful for a specific type of machine learning models, whereas the model-agnostic can be applied to different classes of machine learning models. Lastly, I want to mention recent literature in engineering applications of machine learning models that focus on interpretability. For example, the first paper here evaluates the interpretability of machine learning models to predict fire resistance of concrete columns. The second paper applies Shapley to interpret machine learning models that can predict seismic performance of concrete walls. And the last paper employs ALE to interpret support vector machines that can predict seismic performance of concrete structures. Now, with this introduction, I would like to pose three questions. First, how can we create interpretable models that the seismology community can trust? And the second question is that knowing that there is a trade-off between model flexibility and interpretability, the second question is whether low fidelity, high interpretable models are more appealing to the community than high fidelity models that might be more accurate but harder to interpret. And moreover, along the same lines, can we quantify a threshold for accuracy that the model developers are willing to sacrifice for interpretability? And finally, the last question that I would like to pose is that the more flexible and high fidelity models such as deep learning often require large data. Do you think that this can be a barrier to the application of these models? Thank you.